All right, let's dive into a concept that feels like it's pulled straight from science fiction. We're talking about a laser, but it doesn't shoot light. It shoots beams of one of the most bizarre and mysterious particles in the entire universe.
Just think about that for a second. Imagine you want to send a signal from, say, New York all the way to Sydney. But instead of bouncing it off satellites or running it through cables at the bottom of the ocean, you just point it straight down and beam it right through the planet's core. It's a wild idea, right? But this is exactly the kind of thing a neutrino laser could, in theory, make happen. So how would that even be possible? Well, to understand that, we have to start with the neutrino itself. So, to get our heads around a neutrino laser, we first need to get to know the star of our show, the neutrino. And there's a reason scientists call it the ghost particle. A very, very good reason.
It is honestly hard to wrap your head around just how many of these things there are. They are absolutely everywhere. They were forged in the Big Bang. They're constantly being made in the heart of our sun. And right this very second, trillions upon trillions of them are zipping through your body, through me, through the walls, the floor, everything, without leaving a single trace. Now, that ghostly nature is what makes them so cool, but it's also what makes them incredibly difficult to work with.
And that gets us to the big problem. If we actually want to study neutrinos or, use them for something, we have to make our own beams of them. And our current methods, well, let's just say they're not exactly subtle. We're talking about massive, building-sized, super expensive facilities just to create a stream of these little particles. And this is the exact problem a team of MIT physicists wanted to crack with a much, much smaller idea.
So their proposed solution doesn't start with bigger machines. Nope. It starts with something incredibly, ridiculously cold. A state of matter that only shows up at temperatures colder than deep space.
This thing is called a Bose-Einstein condensate, or a BEC for short. And it is one of the weirdest, most exotic states of matter in the entire universe. Basically, if you take certain kinds of atoms and cool them down to just a tiny fraction of a degree above absolute zero, quantum physics goes into overdrive, and they completely stop acting like individual particles.
The best way to picture it is like this. Instead of a rowdy crowd of individual atoms all doing their own thing, they all lock together and start behaving like a single, giant, unified quantum object. So the physicists started thinking, hey, maybe this bizarre state of matter could be the key to finally taming the neutrino.
Their first idea was pretty straightforward. Okay, so we know radioactive atoms decay all on their own and release neutrinos. So the thinking was, what if we take some of those radioactive atoms, freeze them into one of these BECs, and see if that special quantum state somehow makes them decay faster, giving us more neutrinos more quickly.
But it didn't work. When they ran the calculations, it turned out that just putting the atoms into that quantum deep freeze, well, it wasn't enough. It didn't speed up the decay at all. It was a total dead end. Their first brilliant idea was a bust.
But here's where it gets interesting. Years later, the team came back to the problem, but this time they had a new ingredient, an idea they borrowed from a totally different area of physics, quantum optics.
That new ingredient is a phenomenon called superradiance. In simple terms, it's about getting a group of atoms to act together. If you can get them all in sync, they can release a burst of light, photons, that's way, way more intense than if they were all just acting on their own. It's basically quantum teamwork.
And this was the big eureka moment. The physicists realized that the exact same math, the same quantum mechanics that describe a bunch of atoms spitting out a synchronized burst of light could also describe radioactive atoms spitting out a synchronized burst of neutrinos as long as they were already unified in that supercold BEC state.
So here's how it all clicks together. You combine the deep frozen BEC with this principle of superradiance, and what you get, in theory, is a way to make all those radioactive atoms decay at the exact same time, perfectly in sync. So instead of a random trickle of neutrinos, you'd get this powerful, focused, coherent, laser-like pulse.
And when they actually ran the numbers on this theory, the results were, well, they were nothing short of dramatic. The difference in speed is just astonishing.
So the team used a specific element for their calculations, rubidium-83. Under normal conditions, its half-life is 82 days. That means it takes 82 days for half of a sample to decay. But in their theoretical neutrino laser, that same process would happen in just a few minutes. That's an unbelievable speed up.
And what's really amazing here is that these calculations were based on trapping and cooling about 1 million atoms. Now, a million might sound like a huge number, but in the world of atomic physics, that's a pretty small, totally manageable cluster that you can easily create in a lab. And that detail is what pulls this whole idea out of pure theory and into the realm of things we could actually build.
Okay, so this is a beautiful theory. It looks great on paper, but what does it all mean for the real world? Why should we care? Well, the potential uses are seriously cool. Besides the whole sending messages through the Earth thing, which is already wild enough, a small neutrino source could be a game changer for medicine. The decay process creates very specific medical radioisotopes, the kind that are critical for things like PET scans and even some targeted cancer treatments, but this could create them in a much smaller, way more efficient package.
And here's the best part. We might not have to wait decades to find out if this thing actually works. The goal isn't some giant new particle accelerator. It's a small tabletop experiment. The plan is to actually trap some radioactive material, cool it way down with lasers, and then just watch and see if it spontaneously kicks off this super radiant decay process.
And I just love this quote from one of the researchers. It just perfectly captures the spirit of science, right? The theory's done, the math checks out, and now it's time to ask the universe if they got it right. If they did, a whole new field of physics could just open up.
This project is just a perfect example of how science works at its best. Taking two totally separate ideas, one from atomic physics and one from optics, and smashing them together to create a potential breakthrough. The ghost particle has been so hard to pin down and control for so long, but maybe, just maybe, we're finally on the verge of making it talk.